In the next subsection, I want to talk about the Boyer-Moore algorithm and how it, in a sense, beats the optimal Knuth-Morris-Pratt algorithm. If that sounds weird, you have all the right to find that weird. As I just said in the previous subsection, KMP is an optimal algorithm, so how could you possibly have something better than that? And the sense in which you can beat it is to look at what optimal means. I like to stress this because optimal is a term that's very often used and overused in computer science to mean different things. And whenever someone says something is optimal, be a bit skeptical and ask, what exactly does that mean? Look into the black box. And here optimal means the worst case over a text of length n and a pattern of length m needs at least n plus m time to read the text and the pattern. That's what I just motivated. An adversary could otherwise change the outcome by flipping a single symbol. And no correct algorithm can avoid looking at all symbols in that worst case. But there are many specific cases, like this text that contains only A's and the pattern that is just a row of X's, where there are no matches, obviously. This is, with one look at it, you can tell as a human. But also an algorithm can prove to you, can certify that there is no match with only 4 comparisons. Namely these 4. I compare this position in the text with the last position in the pattern, and similarly here and here. And with only these 4 comparisons, I can prove that there is no occurrence of the pattern in the text, because if there was one, then the pattern would have to overlap this position, or this position, or this position, or this position. Any possibility how you can shift the pattern along below the text would overlap at least one of these positions. And all of them contain an A, which is not the right letter for the pattern, where we have an X, obviously. So none of these possibilities really is still there. So you proved that there's no possible position for a match. And notice that we read, well, 8 characters, 4 in the pattern, 4 in the text. And the text is, I don't know how much longer, and the pattern is longer than this. So we haven't read all the characters, yet we could prove in this case that the output of the algorithm is correct. No matches. And something similar is not, so this is, I mean, this example is far-fetched. This is an extreme case. You might not usually have this, but something not too dissimilar from that is quite frequent. And this is what the Boyer-Moore algorithm can exploit, whereas Knuth-Morris-Pratt essentially uses the same running time n plus m for all inputs, even for this one, where it seems it leaves a lot of potential on the table. One observation from this example is, look that I chose this position and this position. That is the last position in the pattern here. And that seems to be a much smarter way. Had I chosen the first position, I would at least need one more check. And here, because well, the length of the text and the length of the pattern doesn't nicely divide, you have this extra comparison here to just exclude one more position of the pattern. If this was a bit longer, then you see that you waste much less. So starting with the last character in the pattern seems just much smarter. And that's the core observation of the Boyer-Moore algorithm. It's incredibly simple if you think about it. Just do the same thing as we did before, but instead of starting from the left, you start comparing from the right. Incredibly simple idea, but it turns out this is really a very influential one. If we're very lucky, then the last character, as in this example, already is a mismatch, and it is of a kind that I can directly exclude all the other potential positions. So the pattern cannot lie here, it cannot lie here, and it cannot lie here, and it cannot start here either. That one, okay, I somehow messed up with the line lengths now. Yeah, it cannot start here and then starting here would have to end here. Well, counting to 5 seems a bit challenging. But one mismatch here excluded a whole bunch of potential shifts. Okay, so how can we make this work? We could start with just doing the brute force method, but instead of comparing from left to right, we compare right to left. You can think about this offline if you want. It turns out this is not going to work well. If your text looks like this and the pattern like this, then you will essentially have the same worst case as the brute force method, the original one. So you have to do slightly more to get this idea to work. And you have to make bigger shifts, that's for sure. One very intuitive idea is the bad character heuristic. And that means that's essentially what we've done in the example. If you have the text and the pattern, and there was a mismatch at a certain position, you start comparing from the right. But then here, these were not the same. So there's a, I don't know how to draw this, maybe a little lightning. So there's a mismatch here. Now, there will be a certain character in the text, say it's a C. And if that C does not occur anywhere in the pattern, we can already shift the pattern right behind that position C. That's this first case. In the second case, if C does occur, but say only here, then we have to shift the pattern forward so that this occurrence of C, the last occurrence of C, nicely aligns with this C that we found in the text. Okay, so you make this align in that way. That's a very intuitive thing to do, and that's directly generalizing what we did here. There was a mismatch here. A doesn't occur in the pattern, so we shifted completely behind this current guess. You can do just the bad character heuristic. That is sometimes called the Boyer-Moore-Horspool algorithm. Let me move me to the other side. I'm just mentioning this because this algorithm works surprisingly well. It's very simple. Just using the bad character heuristic gives you most of the benefit from Boyer-Moore in many cases, but not in all cases. If you just do this, there's still worst case inputs where you're doing essentially as bad as the brute force method. So what Boyer-Moore came up with is a second heuristic, and that's the good suffix jumps. And these are somewhat similar to what the Knuth-Morris-Pratt algorithm did. You try to use the self-similarity in the pattern to shift things forward. So in the Knuth-Morris-Pratt algorithm, we tried to find a suffix of the prefix that we're currently looking at. And here it's a bit different because we're matching from right to left. But in a sense, this is, we'll look at this in more detail. It's the generalization of what Knuth-Morris-Pratt does if you start comparing right to left. Okay, that gives us two rules. They both suggest an amount that by which we can shift the pattern, and we just use the bigger of the two. In code, this looks like this. We'll go into a little more detail how to compute these magic rules here, the last occurrence and good suffix rules. The code then itself is very simple. We have the current guess I. We iterate through that, or we keep going as long as we haven't reached the end of the text. And we start comparing from the right. So we initialize the position in P to the last one, m-1. And as long as we haven't seen all of the pattern, we start comparing the next character, going right to left. Right to left. And if we ever find that we could complete this while loop entirely, we return the match. And otherwise, so this is the interesting case now. That's the only big difference from the right to left brute force way. Otherwise, we update I to I plus this shift. And so we either have this last occurrence shift or this good suffix shift. And we'll now see what's behind these in a little more detail. The first thing we'll look at is the bad character heuristic. And here I just want to show some examples. So we have a text, where's Waldo? Or where's Wally, I guess it should be in the UK. These are these children books where you have to find this character. To not violate copyright, I'm not showing pictures. But let's suppose you're actually looking for Aldo and not Waldo. Because you're a weirdo, I guess. You start comparing from the right. The pattern has an O, but here we find an R. R does not occur anywhere in the pattern, so we can shift it entirely behind this current character. Okay? The second thing happens here. W doesn't occur anywhere in the pattern, so you shift the pattern entirely behind this. And now finally you find oh, that's a match. So you compare right to left until you find indeed here an entire match. And well, if you want to count, then there's 6 characters of the text that you actually didn't have to look at. Another example where we have the second case of the bad character heuristic. We're looking for more in Boyer more. And so again, we start as before. We find an R here, so that's a mismatch. But we have an R in the pattern, so we only shift as much forward to align this last occurrence of R, it's actually the only one here as well, with the R we found in the text. And so the parentheses here mean we don't have to compare again. We already know that there's a match here. But it's to no avail because the last character is a mismatch. So there's not an E but an M in the text. So we check M. It occurs in the pattern, namely at position 1. So that's the last occurrence of M. So we shift the pattern forwards to align that occurrence with the M in the text. There we go. And now we start comparing right to left. And of course, in this case, we find an occurrence of the pattern. And again, there's a couple of characters we never needed to look at. I think this part of Boyer-Moore is fairly intuitive. It's also fairly easy to code it up. What you can do is you pre-process the pattern and the alphabet, and you compute this last occurrence function. That is simply the index in P where the last occurrence of this character is. And well, if there's no occurrence, then we put a -1 to indicate that. So one more time to show an example here. But I guess the concept is simple. You have this table, lambda of C, and all other characters in this alphabet. So we need to know what the alphabet is up front. And remember, if this is Unicode, this could be 140,000 characters. So you better have a smart way of encoding this. But maybe you can restrict to just the Latin alphabet for now. And then you put -1 for all of these. And for the others, you just find where is the last occurrence. So a smart way to do this is go through the pattern left to right and write the current index at the position of the character. So we are at 0, we write 0 at M. We have 1, so we write 1 in O. But then we have O again, so we write 2 in O. We overwrite the old value 1. And by that, you automatically get the last occurrence. R, we put a 3, E, we put a 4, and that's it. And so to see that you get exactly this shift that I think I've shown green before. So that's this. To see that that matches out in the example, well, you find a mismatch here. You check the last occurrence of R. Lambda of R is 3, as indicated here. So what you compute is J. That's 4, because we're in the position 0, 1, 2, 3, 4 of the text. Sorry, of the pattern. And we're in the guess starts at position 0 in the text. So what we shift I forward is by J minus this, and that was 3. All right. So we take the character at this position, R in the text, look up what lambda is here, and then shift forward by 4 minus 3. All right. So the last occurrence function can easily be computed and can be stored in this array. It needs space proportional to the size of the alphabet, but if you think back to dictionaries and symbol tables, there are alternatives if space is a concern. Now, the second thing I want to look at is the good suffix heuristic, and this one is a little more complicated. I will not give you the full detail of how to compute it as pseudocode, because that's a little finicky and also beyond what I want to give you. I want to give you an intuition how this works. We've gone through the details for KMP, and the only thing I really want to get across to you guys is that it's a similar idea, but you have to adjust the details. And we'll leave it with that then. But let's look at examples to see what the good suffix heuristic is. Suppose you have this pattern, cells, shells, which has self-similarities, obviously. In particular, this substring else occurs twice, here and here. Now, suppose the text is Sheila sells shells. So we do have an occurrence of this pattern, but we won't get that far yet. We put the pattern here, we start comparing from the right, and then we find a mismatch at this position. We find an S instead of the H in the pattern. So what we would like to do is keep this good part. Maybe I should use blue to be consistent. This is a good suffix. We want to keep that. We found that in the text. It occurs here in the text. These are the same, right? So we want to shift the pattern only to positions where these matches are preserved. And in that example, it means we should align the first occurrence of else with this occurrence of else in the text. So this is what we do. We shift the pattern forward to align this else. So this else now is the first else. And then we start comparing as before. So that would have been start comparing at the right and actually find that there's a match here, but that part we'll skip. There is a second case for good suffixes, which is why this is a little more finicky in the details. A different pattern, ode to food, and the text, I like food from Mexico. Yep, I inherited these examples from a colleague from Mexico who sadly passed away a couple of years ago. So this is kind of kept in as a tribute. But that's beside the point. We have found food here, but then there's an E in the text and the pattern had O. So we do have a good suffix here. And we try to find another occurrence of this suffix in the pattern. But obviously there is no other occurrence of food in ode to food. The only thing we find is that a suffix of the good suffix occurs as a prefix of the text. So we can still preserve some of these matches, but only really these two. So we shift the pattern forward like this. So we could still rescue some of these occurrences. And what's more important, any shorter, if I had shifted the pattern by not so much, say only up to here, then there would have been a mismatch implied by the good suffix I already know. So there's no use in testing this. Okay. And well, then again, I would start comparing from the right to find whether there is an occurrence in the text, which in this case there isn't, but that's beside the point of this example. The crucial ingredient here is that we find the longest suffix of the matched suffix, that's the good suffix, that occurs earlier in P. And this longest suffix, in the easy case, it can be the entire good suffix, and then it might occur in the middle of the pattern, like in this case, else was not at the beginning. The other case is only a suffix of the good suffix occurs, but then it has to be at the beginning of the pattern. So much for the good suffix heuristic. To summarize this part, we can compute the good suffix heuristic I'm not sure if I want to give the full details here. I didn't tell you what the number in this gamma array is. So what we look at is the situation we've had a match occurred. So gamma of j means that we have a suffix starting at j plus 1 of the pattern in the text. But if I try to do the jth character in the pattern, we get a mismatch. So that's why gamma j stores a shift where the search first failed. All right. Now gamma j is so j is the first mismatch that we had. Gamma j is a shift by m minus l, where L is we try to find the largest overlap part here, so that we can find either the matched part as a substring here, as a suffix of this prefix. So the pattern that's the good suffix, this one. We have the good suffix, and we have a prefix of the pattern of length L. And now either this good suffix is a suffix of this prefix, or the prefix is a suffix of the good suffix. That's a lot of mind-twisting suffix and prefix. Essentially, the two cases are the same as we've seen in the example. And so this is the precise definition what gamma is. And with that definition, it matches the pseudocode I initially showed. But I actually don't want to give more details on this, or I don't want to show the detailed code how to compute it. I only want to mention that you can compute it in linear time, linear in the length of the pattern, with similar tricks to the COMP failure function. Indeed, you can compute the actual failure function for the pattern and the reverse pattern, where you just read it right to left. Because we read right to left here, maybe this is intuitive. From those two things, you can compute gamma somewhat easily, but understanding all the details is maybe beyond the scope of today. So also for the exam, you don't need to know the exact values. The only thing I would ask you is, given an example like this, what is the shift that the good suffix heuristic would imply? Okay, that's what you have to know. Basically, what we did in these examples, that's what I expect you to understand. The nitty-gritty details of this definition, I don't think is important for this class. That brings me to the discussion. We've seen the Boyer-Moore algorithm with the two heuristics, last occurrence and good suffix. There's a very subtle point to be made about its worst case running time. As it is given, the code actually has a bad worst case. It's as bad as the brute force method in terms of the theta class. And that essentially comes from when we want to repeat all occurrences. The code as given doesn't remember implied matches in the middle. If you look at this, for KMP, it was easy to get all matches without much modification. Remember, we just had this failure automaton, and you can basically add the failure link of the last state, and then you can keep scanning the text. No big difference. For Boyer-Moore, it's a bit of a hassle because you have to, if you have an occurrence of the pattern here, and then you try to shift it over, then you would have to deal with these matches, but you start comparing from the right. So you can get disconnected parts in the pattern that are already matched. And unless you keep track of these, you will not get below the n times m worst case. But that said, unlike for the brute force method where this can easily happen, for the Boyer-Moore algorithm, you have to search really hard to find an example, and they're really more isolated. Also, if the pattern does not really occur in the text, you always get a linear time, n plus m plus the length of the size of the alphabet, because that's time you need in the pre-processing. So this is not at all obvious. It's a very complicated analysis behind this statement, but it's still very useful to know that if the pattern does not occur, Boyer-Moore is essentially optimal as well. The other statement to be made, if you look at typical English text and typical phrases that you might search, so the text is English text and you search for a pattern that is English words, then you really only look at a quarter of the letters as a rough figure. And that's quite interesting. That means it is probably 4 times faster than KMP if number of comparisons is the main thing. And that is indeed what people find in practice. So many implementations where you're looking for patterns are built on the Boyer-Moore algorithm or modifications thereof, like the Boyer-Moore horseball I mentioned. And even though some of these do not care to get the best possible worst case, they're usually much faster than KMP in many applications. And that's good enough for some of these cases. Another positive thing is the space usage is moderate, but it still has this dependency on sigma, which can be problematic. To finish off the Boyer-Moore part, I want you to get active again. So here's a question about this algorithm, where I'm basically asking you to compare these two algorithms. So you have to precisely read the statements and only take those where it's clearly correct, where it's clearly true. And yeah, some of the answers are pretty clear from what I've just said. For others, you have to think a little more deeply. Let me move over to this. And we've had some 30 voices, so I would like to see at least 25 as often before I want to reveal the answer. Come on, guys. Think of the important participation marks, the little percentages. They're all for free. You just have to vote. I didn't put an option. I have no clue, but then you might just guess. 22. 24. We're getting there. Okay, see people changing their minds. There we go, 25. 27, brilliant. So almost all of you got this second part. Let me maybe switch back to this. Yes, Boyer-Moore is faster than KMP for some inputs, and that's precisely the motivation of this subsection. It happens to also be the other way around, and that essentially follows from the worst case. At least as we've discussed, the Boyer-Moore version we've discussed has this bad worst case, whereas KMP is always n plus m, so there must be inputs where it's the other way around. And a more subtle statement is the last one, but it's also true. If there are no matches, then Boyer-Moore is never worse than KMP. And the reason for that, again, is we're only counting symbol comparisons and ignore the pre-processing. And there, Boyer-Moore is just never doing more than Knuth-Morris-Pratt. They might be actually the same for many examples here, but that's a different story. It's only claiming less or equal. Okay, thanks for that. And that concludes Boyer-Moore, the usual choice for string matching in practice.